Okay, so people are joining us, but I think as opposed to the two last times, I'll just begin and people will join us throughout. Okay, so hello to you all. You see my screen, that's good. This is our third lecture. Last time we talked about Cyrilson's problem. The lecture before that, we talked about the complexity class MIP star and the challenge of bounding its power. Today we are going to talk about Cohn's embedding problem. I want to dedicate this talk to my grandfather who died this morning. Tzvi was a writer and a professor of literature at Bar Ilan University. He raised 5 children and he was a great grandfather. And I loved him very much. So this one is dedicated to you, Tzvi. Oops. Okay, so as I said, today we talk about Cohn's embedding problem. At our first lecture, I tried and I wrote down the implications between these 3 problems, stating that every language in MIP star is decidable, stating an inequality in Cyrilson's problem, and what we will talk today about
Can
is...
I steal a second and make a personal comment? I mean, it's people don't know, but this name Luz says a lot to people my generation. So Michael's great-grandfather was the first speaker of the Knesset, a legendary person he was. I won't tell more than this, but look up Kaddish Luz if you're interested. So he was the father of Tzvi, right?
Yeah, this is true.
He was his son, yeah, okay. Sorry.
Yeah, he's on the picture on the back, if you see on the left there's Kaddish.
I can even recognize his picture.
תודה מיכאל שאתה נותן את ההרצאה ביום כזה.
תודה לכם שאתם באים להקשיב תמיד. Okay, so although personally this is a more important thing, I think I'll go along. Okay, so as I talked about at the first lecture, and during the second lecture, we said that if Cyrilson's problem was an equality, we saw that it would have implied, so equality here, would imply that every language in MIP star is decidable, but we saw that this is just not true. Okay, because MIP star is equal to RE, and in RE there are languages that are not decidable, specifically the halting problem. So it means that this thing is an inequality. So this is a strict inclusion, if you remember what we talked about last time. Today I'm going to approach Cohn's embedding problem. Now, in Cohn's embed, I will use Slofstra's way of introducing this problem, because when you look at it as Slofstra introduced it, you will see immediately that if you construct a game that separates, a nice enough game that separates between the set of quantum approximated correlations and the set of quantum commuting correlations, you automatically see that Cohn's embedding problem is refuted. So the conjecture is refuted. So this is the approach that I'm using today. So let's dive in. Let's talk about Cohn's embedding problem. I talked a bit about the definitions last time, but I think I'll go through them again because we were only able to go through 2 slides. Okay, so what is an algebra? An algebra, again, is a vector space. All our vector spaces will be over the complex numbers. So from now on, it's a complex vector space. And it has a bilinear multiplication law over it. If it is associative, we call it an associative algebra. If it has a unit, multiplicative unit, we call it a unital associative algebra. And from now on, all our algebras will be such. 3 examples that we talked about last time. the n by n matrices over the complex numbers are an algebra together with the regular matrix multiplication. A straightforward generalization of this thing is the bounded operators over a Hilbert space. So this is the second example here. Oh, I will maybe use the pointer. Oh. Just a moment. I think my pen needs a moment to be connected to my iPad.
So while you're doing it, Michael, all three are associative and unital, right?
Yeah, exactly. So these are just 3 examples of this thing. Let me try and disconnect and connect again. Sorry for that. Great. Okay, you see what I'm. Okay, so BH is just a straightforward generalization. It's the bounded operators over a Hilbert space. And yes, again, there is the identity operator, which is bounded. So it is unital and clearly, how do you call it? When you do operators one after the other.
Composition?
Yeah, composition of operators is associative. So clearly this is an associative unital algebra. And another interesting example that is very interesting for those of us who are interested, who care about groups, and I will talk about a bit about groups today, is the group ring, the complex group ring over of a specific group G. Let's think of a discrete group G. And each one of these examples has another operation on them. So they have this adjoint operation, which is sends the identity to itself, so it preserves the unit. It's adjoint linear, so the coefficients go outside with the complex adjoint. It's multiplication reversing, and it's involutive. So if you do it twice, it's the identity. And algebras with such an operator, so unital associative algebras with such an operator will be called star algebras. And from now on, all our algebras will be just these unital associative star algebras. So I will not say unital associative star algebras, just algebras from now on. Great, so this is like the beast that we are handling with today. And as with most algebraic structures, there is both the notion of homomorphism and the notions of quotient. So let's review it quickly. If we have 2 algebras, a linear function between them that also satisfies the following 3 rules is a homomorphism. Okay, so what are the additional 3 rules? So it preserves multiplication. It sends the unit to the respective unit on the other side. And it preserves the adjoint operation, the star operation. And an example, a very natural example, is this specific embedding of the 2x2 matrices in the 4x4 matrices, just as block matrices on the diagonal. And we discussed last time that, for example, if you would have embedded it in this way, it will not send the unit to the unit. And if you would have embedded it this way, it won't be linear. So it is, you need to be careful a bit in the way you do these kinds of things. And later on, we will see that actually this specific embedding preserves another thing. So it also preserves the normalized trace of these matrices. And this will be an important point later on. So I just pointed out. Okay, so if you have an algebra, you can talk about a specific vector subspace, a linear subspace I, and we call such a subspace an ideal if it also satisfies this condition, that is, it is closed under left and right multiplication from the big algebra, and also it is closed under the adjoint operation. And when we take a finite set of elements, we denote by this tuple of elements in round brackets, the smallest ideal containing all of them. And this ideal is called the ideal generated by them. Great, now when we have an ideal, we can talk about, so specifically it's a vector subspace. So we can talk about the quotient, and this quotient has a star algebra structure, a natural star algebra structure coming from the big algebra. So this is just the quotient. Okay, now we can talk about finitely presented algebras. So usually when we use commutative rings, we know that every finitely generated commutative ring is just a quotient of the ring of polynomials. And okay, and it depends exactly what, again, what is the context, but in our context, we talk about algebra, so these are vector spaces. But usually when you use matrices, they do not commute. So a more natural thing to do is to talk about non-commuting polynomials. So first of all, the big thing will not be regular commuting polynomials in k variables, but will be non-commuting polynomials in k variables. But again, this doesn't have a natural star operation over it. So we just add k additional symbols, x1 star to xk star. And then we can just extend anti-linearly the involution that sends x1 to x1 star and x1 star back to x1 and so on for every generator. And this is now a star algebra. So this now satisfies all the requirements of a star algebra. And we will denote it by C star of x1 up to xk. So note that x1 of up to xk is polynomials in 2k variables and not in k variables. Okay, so now we can define what a finitely presented algebra is. A finitely presented algebra is just a quotient of this algebra, this C star of x1 up to xk, by an ideal generated by a finite number of polynomials. So this is just the definition. And we denote it in this form, okay? It's a bit similar to the way we present finitely presented groups, but we write the C star beforehand. Great, so 3 examples. The first example is the algebra of a unitary. So what is a unitary? It's an element that is, the conjugate of it is the inverse of it, right? So we can just say, let's look at all polynomials that are generated by u and u star, such that u star times u is equal to u times u star is equal to 1. So we actually define the f1 is u star u minus 1, and f2 is u star minus 1. And these are the 2 polynomials. The ideal generated by these two polynomials is the one we use here. Okay, we can take the algebra of a projector. So last time we talked about operators that satisfy this relation, okay? So their square is equal to themselves and they are self-adjoint. And we said that these kinds of operators are called projectors. And we can just define, again, the set of all polynomials that are generated by such a thing. Notice that this is an infinite dimensional vector space, but this is a finite dimensional vector space. Okay, this is just a small note. If this is not clear, just think about it for a moment. The last example that I want to give today, at least for now, is the algebra of an M outcome projective valued measure. So last time we said that an experiment in quantum mechanics is modeled using a projective valued measure, which is some kind of non-commutative analog of a probability measure. And you just need M matrices that sum up to the identity and are all projectors. Okay, and we call it a projector valued measure. We had also the definition of a POVM, but I don't want to recall it for now. And you can note that this algebra is exactly satisfying what you would, like the generators of this algebra exactly satisfy what you would assume a PVM will satisfy. Okay, great. Now we can talk about representations. Okay, so any homomorphism from an algebra to the bounded operators of some Hilbert space is called the representation of this algebra. Now, if this Hilbert space is finite dimensional, we call it a finite dimensional representation. And if this algebra is finitely presented, so it's just generated by x1 to xk with the relations F1 to FR, I just want you to note that choosing a homomorphism is the same as just choosing K elements inside the bounded operators over this Hilbert space that satisfy all the relations. Okay, this is all we need to define a homomorphism. So defining a homomorphism and choosing K elements inside BH that satisfy all the relations are the same thing. Okay, great. So an example is just that you can choose any projector, so any matrix that satisfy these two equations. Okay, and it automatically defines a finite dimensional representation of the previous projector algebra. Okay, so this example. Okay, hopefully this is clear, right? Now I want you to note that at least in this case, it can be an embedding. So you can check that if you choose a specific projector, this map can be an embedding, not only a homomorphism between this vector space and this algebra of matrices.
I'm not sure I understand the last comment.
Okay, so if you choose a projector, you choose a P, large P inside M and C.
Mm-hmm.
Okay, and it defines what I claim now. So if P satisfies P squared is equal to P is equal to P star, mm-hmm. You can just define a homomorphism H from C star P with the relations P squared is equal to P star. This is the small p mm-hmm. into M and C by just sending H of small p to large P, right? Okay. And then P star is sent to P large P star and so on and so forth. My claim is that you can choose large P such that this is an embedding. This is all my claim. Okay, and this is non-trivial. Having a finitely presented algebra that embeds inside the n by n matrices is a non-trivial phenomenon. Mm-hmm. Okay, so now I want to talk about finite approximations of algebra. So I didn't talk about any motivation to Cohn's embedding problem.
Follows that whenever you have such a projection, then the algebra generated by it is a bounded dimension, right? Because the universal one is of some specific dimension if it can be embedded to M and C.
Okay, this is a good point, Alex, and I will return to it in a few minutes, okay? So Alex just stated that there is a connection between the fact that this is a finite dimensional vector space and the fact that we could find an embedding into M and C. Okay, so one way is clear, the other way is not so clear, but we will talk about it in a moment. So this is the definition of a matrix algebra. So up until now, I didn't give any motivation to Cohn's embedding problem, but the context of Cohn's embedding problem is exactly trying to take some algebraic structure and approximate it, whatever that means, using finite dimensional things, okay? So the most clear example is just having an algebra that embeds into the n by n matrices. So if you have this property, you are called a matrix algebra, okay? And this is quite clear. You can just write all of the algebra as matrices inside some for some dimension n. And as we just stated, being a matrix algebra is the same as being okay. So at least for so being a matrix algebra is the same as being finite dimensional as a vector space. Okay, this is just the same thing. So an automatic corollary is that not all algebras are matrix algebras. So the example here, so I stated, I think that this algebra is not finite dimensional as a vector space. So any unitary that you choose will have will satisfy a finite polynomial that is not a relation of this algebra, right? So any n by n matrix satisfies the characteristic polynomial of itself. So you will have an additional relation. So this will not be an injection. So clearly, this algebra is not a matrix algebra. And you can see it from the fact that it is infinite dimensional. Okay, but this doesn't discourage us automatically, because any actual calculation that we do on a specific algebra can be done only on finitely many elements. So if we just want to do a specific calculation, maybe we can model at least this part of the algebra, the part that we care about in our calculation, using some finite dimensional, some set of finite dimensional matrices. And this gives us the notion of residually finite dimensional.
Wait, Michael, can I ask you about so was this a trick or is this a method? Is this how in general you prove that an algebra is not a matrix algebra?
Okay, so you can take this fact, take this fact
No,
as
I
given.
understand.
And
No, I'm asking that proof I understood. I'm wondering if this was a trick or this is a generic way of proving.
Okay, the fact that an infinite dimensional algebra cannot be embedded in MNC, this is clear because MNC is finite dimensional.
Right.
The other way around is not so clear. Maybe I'm not the one to like. Yeah.
It is. I mean, it is clear if you want to think, if you say no, Arkin-Wedderburn theorem, something like that, because
Okay.
Anyway, it's a finite dimensional. Any such finite dimensional algebra is just a product of matrix algebra.
I see. That's right. Okay. Thank you. Yeah.
So, thanks, Alon.
Okay, great.
And we can embed this product.
Be careful. This is for semi-simple algebras, not that it's a product of finite dimensional matrix algebra. For general one, I'm quite sure that every finite dimensional algebra can be embedded into an algebra. You probably just let act on itself let it act by multiplication, I think, on itself, unless you have, what is called kind of, there are elements whose product with everything else is zero. I forgot how they call it.
Annihilators.
Kind of an annihilator of itself. So you see that unless you have elements like that, if you act on yourself, you get an embedding into matrices. There is another slight of an issue here that you want an embedding which would preserve also the star operation. So I'm less sure about that, but I'm sure that this must be known.
Okay, so maybe
it seems that if you just start, it should work, right? If you take an element and find its minimal polynomial, and if it has, if you can write it as a product of other polynomials, or you can try to find elements with smaller minimal polynomials, and eventually you find a minimal element, and then you map it. It should just work, no?
Maybe it does. I didn't prepare a proof for it, so maybe next time I'll bring something. This is very interesting.
Off the trade, but there is something to be understood here, right? It's not entirely...
Yeah, this direction is not clear. You said that if it is like this direction,
right,
is not clear. Okay, but let me move along. Okay, we said that U is residually finite dimensional if any finite set can be separated using using matrices, finite dimensional matrices. So it means that we can find a finite dimensional representation. Again, this is just a homomorphism into MNC, such that any two non-identical elements inside this finite set have non-identical images. Okay, so this is the meaning of separating this finite set. And the fact is that not all algebras are residually finite dimensional. So if you are a group theorist, you at least remember that there are non-residually finite groups. And if you take the C-star algebra, like the group ring with complex coefficients of these groups, you get a non-RFD algebra. Okay, so
for groups, there is another characterization using inverse limits, right? Of residually finite. I forget what it is exactly, but
inverse limits.
Yeah.
Maybe that you mean
Like
that you are
profinite,
injected into the profinite completion.
yeah,
in this sense?
exactly. Yeah.
Yeah, you are injected to
That
your
we have
profinite
Mr.
completion.
Profinite here with us, no? Alex.
Yeah, Alex can probably say more, but
No.
the point is that there are, the only point that I care about here is that there are non-residually finite dimensional algebras, and
No, take a finitely generated discrete simple group and take its group algebra, then
yeah,
it does
exactly.
not have any.
Wait. Alex, tell us in a way that we all understand.
If you take a finitely generated, say, simple group, there are groups like that.
What do you mean, A5?
No, infinite.
Okay.
Infinite simple groups, right? There are finitely generated. This is slightly less trivial to construct, but it's well known that there exists such. Now, every representation of such a group must be trivial, because a finitely generated linear group is residually finite. Namely, and in particular, it has a lot of finite quotients, but a simple group cannot have finite quotients. And therefore, if you look at the group algebra of such a group, every finite dimensional representation of such a group algebra is also trivial, because it must send the elements to the elements of the group to the trivial element.
Yeah. Okay, so I gave here an example that is not simple, but at least has no finite quotients, and I think this suffices for what Alex just said, right, Alex? Like, yeah. This is the Higman's, like, this is the group algebra of the Higman group. So you just
are we supposed to say that it has no finite quotients?
No,
yeah,
it's not difficult, but it's not completely trivial.
It's not completely. Yeah, but it's not a hard exercise. Like, probably you can do it.
It's a smart exercise. Let's put it this way. I cannot think about that unless I saw it. I don't know, 40 years ago.
Okay.
Give us a hint. How do you prove it? Just a hint. No, don't do the whole exercise.
Well, if you think I remember, I remember that you look at the mod 2, you look at this, the order of the elements, assume you have a finite quotient, and then follow up what is the order of you see, because x2 and x2 square, for example, are conjugate, they must have the same order. Okay. This is in principle possible.
Yes.
For two groups, but it means that each one of them must, that this element must have an odd order, right? Because if it would have an even order, then then its square will have that.
Some power would break. Okay.
Right, and then you look at the order, or I think the game is to look at the order of two modulo in the field of in the modulo that number L. So I don't know. I don't remember now.
Okay, I apologize for the Hebrew, but this reminds me of the Gashash. לך תזכור מה עשינו ב-48.
Well, usually I remember 40 years ago better than yesterday, but early for me in the morning.
Okay, so I'll go over, but the point is that we could have dedicated like 10 minutes or so to prove to you that there are non-residually finite dimensional algebras. Maybe we will do it later, but at least for now.
No, but Micha, the question
is an example.
Really, I don't want to derail you, but if this is just for general impression, that's fine. At least for me. But if this is stuff that you're going to rely on, then I would be much happier to see a bit.
No, the main point is that you would have liked your algebras to have some notion of finite approximation. And the easiest notion of finite approximation, just being embeddable inside the matrices, is too weak. Okay. The point is, even if you want to only separate every finite set of elements inside your algebra, this is also like too many algebras don't satisfy this condition. Okay? And the question is, maybe there is a generalization. What?
Yeah, so let me understand. So I think at least I understand the principle. We're trying to understand the notion of finite, like finite, and you say here one notion which is very natural, too weak, slightly stronger or slightly more general, also still too weak. That's the
Yeah,
story.
that's the point, right? Thanks
Okay.
for this clarification. Okay. Now the point is that last time, like in the previous slide, I wanted to separate every finite set out of the algebra, and we said this is not possible. But maybe we can do it not with not using representations, not actual representations, but something like an approximate representation. So we will choose a finite set of matrices such that they almost satisfy all the conditions of a homomorphism. So they almost satisfy that they the star operation, the star thing is going to the star, and they almost satisfy they almost respect multiplication, and they almost respect addition, and so on and so forth. And the way we do it depends on the choice of a metric over the n by n matrices. So when Alex gives these kinds of talks, usually he says that there are many interesting metrics, norms, over the n by n matrices. And this is very true. There are many notions of distance on the n by n matrices, but at least today we are going to choose only one of them, which is the one Kohn used, which is the Hilbert-Schmidt norm. Okay, so let's recall what the Hilbert-Schmidt norm of a matrix is. It's just taking the adjoint of A multiplied with A, taking its trace and dividing by n, and then taking the square root of all this thing. And note that at least this number is the sum of squares of the entries. So this is some kind of a normalized 2 norm over the matrices. Okay, so there is a reason why we choose this norm. It's highly related to what's called the GNS representation.
Wait, the sum of squares
like
or the sum of the sum of squares or the sum of squares of absolute values?
Absolute value.
Yeah. Right. Sum of squares of absolute values. Okay, so thanks. Great. So this is that definition. This is our metric. And now we can define what an approximate representation is. So for any epsilon, we can define, again, I will just call it an epsilon representation, but the more correct, the better way to call it is a finite dimensional pointwise epsilon representation. And I define it only, notice that previously I defined representation for any algebra, but here I'm defining an epsilon representation only for finitely presented algebras. So if U is given as a finitely presented algebra using these generators and these relations, we call a tuple. Notice this is not a map. This is just a tuple of matrices, A1 up to AK, inside the n by n matrices. We call it an epsilon representation if it satisfies that for any relation, if you take these matrices, these A1 to up to AK, and you put them inside every relation, it's the norm of it, okay, and now this is the Hilbert-Schmidt norm, is smaller or equal than to epsilon. Okay, so I'm just choosing images of the generators, and I want the images to almost satisfy all the relations when I use the Hilbert-Schmidt norm.
So this definition depends on how you choose to write U in some sense.
Yeah. So I'm already giving you a specific presentation, finite presentation of U. You are correct. It highly depends on the presentation. Although any epsilon representation using one presentation of this algebra is a maybe epsilon prime presentation, representation using a different presentation of this algebra. Okay, so changing the presentation only changes the epsilon.
Yeah, and epsilon prime goes to 0 together with epsilon, I guess.
Yeah, exactly.
And if you would have required that this holds for any, I mean, you could have somehow extended this to all elements in the group, no?
The algebra, yeah. The word
algebra.
pointwise here means that you cannot extend automatically to the whole algebra. The point is that for any finite set of elements, okay, so it will be important in a moment, but now I just defined what an epsilon representation is, and it's only on generators, which means that the exact epsilon, you would have liked me to say something like the following. So you define the map from C star of x1 up to xk with relations f1 up to fr into m and c, such that phi of x plus y minus phi x minus phi y is in Hilbert-Schmidt smaller than epsilon, and that phi of x times y, phi of x times y minus phi x times phi y is smaller or equal to epsilon, and so on and so forth, right? So like the star operation needs to go to almost the star operation and so on. But the problem with this definition that it is too strong of a definition. Like this is called usually a uniform epsilon representation, and this is a pointwise one, and there is a slightly different way of looking at this thing, and then there is you can change the quantifiers in some other definition, and you see that in one direction this is the uniform definition, and in the other direction it's the pointwise definition. So this definition can look like another natural thing, but this is not the one we talk about today. Okay.
Does this one imply the weak one?
Yeah, this is a stronger notion. Clearly, this is a stronger notion. But you would, okay, so during this seminar, we will talk about something called stability. And stability asks whether an approximate representation is close to an actual representation. Okay, and this will be very important in our seminar because it's used repeatedly in the MIP star is equal to RE paper. And then the correct notion of closeness depends on the definition of approximate representation. Because if you want to be close in the sense of a pointwise representation, you want only to be close on the generators. But if you want to be close in this more stronger definition of a uniform representation, you would want to be uniformly close on all elements of the group of the algebra, again, up to some factors that depend on, I don't know, like you need to add something inside because you cannot be totally uniform because you have scalars, right? You have multiplication by scalars, but you need some other notion of closeness. Never mind. I think this is not very important for now. We will discuss stability later on in the seminar. And also Alex is doing a seminar at Princeton right now at the IIS on this topic every Wednesday. It's highly interesting, and all the talks are on YouTube. So
okay, can you explain why this generalizes the previous one, the residual one?
Wait, I just defined what this generalizes the notion of a representation, right?
Yeah.
Because every zero representation in this definition is just what we call the representation in the previous sense, right? A homomorphism is defined only on the images of only by the images of the generators if they satisfy all the relations. Who right. Talked with me?
Yeah, Itai. Okay. Yeah. That's
Hi, Itai. So now the previous notion was separating every finite set using actual representations. Now I want to, in some sense, generalize this notion and ask, can we separate every finite set using some epsilon representation? Okay, so I'll go to my next slide. So now I didn't write automatically the definition of what a hyperlinear algebra is, but I want us to think of what is the most natural way of defining this thing. Okay, so we have a finitely presented algebra. We say that it is hyperlinear. Okay, we would have liked to say if you can separate every finite set of points using an approximate representation. Okay, so how do we write it?
As an analogy with residual finiteness, right?
Right, exactly. But the point is that what does it mean to separate using epsilon representation? We can just take a huge epsilon and then probably it separates everything, right? Like we can find elements that have small Hilbert-Schmidt norm, and then it doesn't matter what are the polynomials, probably the output will be a very small Hilbert-Schmidt norm. And in such a way, we can do be smaller than epsilon in a non-interesting way. The point is that we want something for every epsilon. So for every epsilon, and for every finite group, finite set in U, this is finite. And before all of this, I want to choose for every U. So we said that this is a finitely presented algebra. So just choose a section. Choose a section of U into C star of x1 up to xk, which just means that there is a projection, not a projection, an epimorphism from C star x1 up to xk onto U, right? There is such a projection, so just choose a representative of every image inside the set of polynomials.
Preimage.
Preimage, yeah, right, sorry. Choose a preimage for every element and just fix it for now, okay? So for any epsilon greater than 0, and for any f, we want the fact that there exists some a1 up to ak inside, there exists an n, right? And there exists a1 up to ak in M and C, such that this is an epsilon rep of U, and we wanted to separate the elements of F. So we need to choose beforehand. So I needed to write, so we need to choose a section, and I need to claim that there exists some function from U to the non-negative numbers such that delta of x is 0 if and only if x is 0. Okay, so it sends to 0 only the 0 element of the algebra. Oh, this is another, yeah. And we wanted to separate the elements. So this function will control, point is that this function will control the separation. Okay, so we want the distance. Okay. Okay, so we wanted to separate the elements of F. So for any F1 is not good. Any G and H in F, we want the following. So let's call the polynomials that we fixed, the section that we fixed beforehand with tilde. Okay, so G tilde of A1 up to AK minus H tilde of A1 up to AK. We want it in the Hilbert-Schmidt norm to be larger than something. Okay, we want them separated. Separated by what? But by the delta of G minus H. So if G and H are the same element, this is okay. It can be 0. But if these are two different elements, so if this is not the same element, we want them to be sent to actual two elements that are bounded away by this function, by this delta function. Okay, so I'll recall really quick the definition here, and then I'll go to the next slide, and then we'll take a break. So we have a function here that the function defines what does it mean to separate elements. This is this delta function. We chose also a section. So for every element in the algebra, we chose a polynomial that is sent to this element. And then we ask that for any finite set and every epsilon, we can separate these elements using an epsilon representation such that these elements are sent to elements that are at least delta of their difference apart. So this is this definition. Hopefully I didn't lose any
I'm not sure
point
what is the role of this delta.
You want to define what does it mean to separate.
Delta hasn't exists before it.
Right, you need to you need to have a function such that this, okay, so the definition of being hyperlinear requires you to define such a delta.
Delta is just a resolution, right?
I'm not sure what a resolution is, so maybe
not
elaborate a bit more.
Just out of the...
Guy, if you want to think about it, it's slightly less technically. Think about what is residue finite, or residue finite for groups or for algebra. That you have representations, and eventually the representations separate the points of the group.
Fine.
Namely, there exists, if you, maybe the best thing you think you have a sequence of representation, and eventually, every element, it is non-trivial, eventually. Because you can take bigger and bigger representations. Now,
okay, but
here you take...
My question is, when do you...
So just a second, let me finish.
Do you pick delta before you pick
Just a second, I'm giving you a definition without delta.
Okay.
So here, what you say that you have a sequence of almost representation with epsilon I, with epsilon n, but the epsilon n is going to, which is going to 0. There are better and better almost homomorphism, and but for every element G which is not 0, you want that it's kind of bounded away from 0. You don't want it to go that the distance between it to 0 is also going to 0, because then it's not a separation. Now here it says G minus G prime, but because we are talking about algebras, yeah, it's enough to separate every element from 0, and then you can move it to separate every 2 elements. So you basically
okay. I want just to say
almost
about
homomorphisms separate the point of the group. You cannot say it on one homomorphism because it's not well defined somehow.
Right. So just to...
Wait, Guy, I just want to add something to Alex's point, because in groups, you can just finish and say what Alex said. The point is that, at least in algebras, you have this problem that something can have a very small operator norm or a very large operator norm, and then you would expect to be separated from 0 in a less, like you can think of this delta as the operator norm or something like that.
Right.
Like things that were previously very close to 0, you can only separate them by their original distance from 0. Okay, this is the kind of way you can think about delta. In groups, all of the elements, for discrete groups, you can think of all the elements as being very far away from one another, and then you can choose a uniform number, like for example 1, and just say that this thing is always greater or equal to 1. Okay, when you define hyperlinearity of groups. But at least for algebras, you need to be a bit careful, because there are things that are very, very, very close to 0 in the original sense, because you can just multiply by a very, very small constant. And then...
Right, so what you're saying, yeah, I understand. But could you have said that delta is a norm on the...
It's a substitute for a norm, right?
My U doesn't have a norm on it yet, right? It doesn't. It's not embedded in any operators on any Hilbert space, and maybe it's not a pre-C star algebra. So if it was a pre-C star algebra, I could have defined a norm on it and so on, and then maybe I could have taken delta to be the operator norm or some norm on this thing. But at least for now, I don't want to say anything about this delta. It can come from a norm. It can come from a different object. I just need a delta.
So I have 2 more questions. First, so technically, the exists before the delta, the exists delta, you choose delta before you choose epsilon, yes, and also before you choose f. Is that correct?
Yeah,
read the definition.
This is some choice. This is some
in front of your eyes.
Ah, yes, right. I was still talking with
about the previous slide. So here it appears very clear.
Now you're looking at the official statement.
Now there's an official version, right? Yes.
So delta really serves as a substitute for norm, right?
Right. So that's my second question. So suppose this is a C star algebra with a norm and everything is nice. Is it true that without loss of generality, delta is the norm in that case? Or are there cases where you need delta to be different from the norm?
I'm not the one to answer this question.
It is more suitable it is more suitable to talk about tracial algebras. Like this Hilbert-Schmidt norm, it shouldn't be similar. This Hilbert-Schmidt norm shouldn't be similar to the operator norm, but to some norm defined by a trace on your algebra. But
okay, so Alon is mentioning the fact that there are many norms on operators, right? We just said that we have here the Hilbert-Schmidt norm, but we also have the operator norm, and there's the Frobenius norm, and there are many other norms, and maybe you didn't choose the correct norm. I think this is what Alon's point is. But I really don't want to get into like delta for us it's a technicality. Alex tried to just throw it out because at least when you talk about groups, you don't need this delta. And groups are a very interesting case of hyperlinearity. But for our algebra case, we do need this delta, and let's just take it as given.
So let me throw in my two cents. Really,
okay.
If this is supposed to be a substitute for residual finiteness, so you want things that should be zero, okay, almost zero, but you should normalize them appropriately. Now, when you have a norm, it's very clear what the normalization is. This should be done with respect to the norm. You don't have a norm, and you have to create a substitute for this. This is what this delta does. It tells you in the vicinity of this element how to quantify what is small and what is large.
Yeah, that's good. Okay, great. So let's take a break. Wait just a moment. I'll just give you a question. When you do this, when you give this definition for groups, the automatic question is, are all finitely presented groups hyperlinear? And before the break, I want you to think about it for a moment. Are all finitely presented star algebras hyperlinear? So let's take a 10 minutes break. So we will meet back on 5:03. And then I'll tell you the answer.
Michael?
Stop breathing now for 10 minutes.
מיכאל?
Yes.
יש הגדרה שקולה עם על מסננים, עם על מכפלות? כמו שיש לה...
אנחנו נגיע לזה, זה בדיוק הנושא של... Okay, so there was a Hebrew question, so I'll just translate it very quickly. The question was, is there a different way of defining it using ultra products and ultra limits and so on? And the problem is called Cohn's embedding problem. So there is some algebra defined using ultra filters and so on, such that hyperlinearity is the same as being embedded in this algebra. So this is what awaits us for the next hour.
10 minutes?
Can you say the definition again of hyperlinear for groups?
Yeah, do the same for the group ring.
But what would be the delta? If I'm just talking about...
So if you care only about, if you take a group ring, all your elements of the group are now unitaries inside this group ring.
So delta is identical.
So the delta, you can just take it to be 1 or something. And you care only about, okay.
So it's just whether the two matrices are the same or not? Okay.
Okay, so I care only about the images of the group, right? So inside this C-star algebra, actually I care only about the images of the elements that come from the group. So my claim is that at least these elements can be separated by 1. Okay, I have...
Michael, this is, I mean, you're right, but I think it's a kind of a trick. You could define, I think, also separated by some delta, and there is some trick in groups, if I remember correctly, that you can change it so that it's separated by 1. At least for Sophic, I think I remember some trick like that. But the natural definition is to say that you are bounded away from 0, that's all. That for every G...
So you say that also for groups you would have liked to have a function, but my claim is that, okay, maybe it's a trick.
In a way you don't need... some of the mentally you want to say that there is no element which is in the common kernel of all this almost homomorphism. The problem is that kernel of almost homomorphism is not a well-defined notion. So the right notion of a kernel is something which converges to 0, right? That elements which are not separated from 0 or from the identity in the context of group. I think, for example, if you will define in the ultra in the ultra.
We will get to the ultra product in a
then
moment.
You see it's exactly the kernel somehow that you can kind of that you have a faithful embedding into the ultra product, and you can.
Yeah, but where? But this and the separation will come from the fact that you actually embedded, and then there needs to be a universal bound.
Because basically, what you can say that the look at okay, so here is a precise definition. Whatever it's a group or an algebra is hyperlinear if you have a sequence of epsilon n representations such that for every G in the group or in the algebra, which is not the identity, I mean, not 1 in the case of group, not 0, the infimum over the epsilon n of G is bounded away from 0.
Okay.
And you can call this infimum delta if you want.
Great. Okay.
But uniformly.
I think Alex.
No, it's not uniformly bounded. No. For every G,
element, it's just one. Okay.
Right. And what Michael stressed to you that in the case of algebras, you cannot
of groups
expect
to be
uniform. In the case of groups, you can. There is a trick which I forgot, but you can make given hyperlinear in my definition. I think you can arrange to change it and to get hyperlinear with a uniform bound.
Okay, regardless of whether it's finitely generated groups or anything, for any group.
For every hyperlinear group, if it's if you have
it. I think Liviu Paunesco said in the chat that this trick is called amplification. Maybe when he comes back, he can say something about it.
Right. Okay. Yeah, there are some experts.
You leave this part in the recording, right? So that we can.
Today I will leave it because I must say that all the recordings are preserved in the Moodle. So to the YouTube, I'm a bit more strict in what I'm uploading, but to the Moodle, I'm not. So you are a HUJI member. I can just add you to the Moodle if you're not added already, and you can see everything there.
Okay, so when do we come back, Michael?
You said that this is not a real break. Okay, so
no,
05.
No, fine. No, just
05. I'll start.
05. Okay, good. Very good.
Michael, are you there? Michael.
Yes, I'm here.
So I think I have a terminology question. In measure theory, algebra is something different, am I right?
Yes.
Are the
Sigma
two...
algebra? You mean a sigma algebra, right?
I mean, even a regular algebra, there's such a thing as a regular algebra is close to finite unions and complements.
Yeah. So the
It's not
definition
the
of
same
an
term.
algebra in algebraic structures is usually a ring, which is also a vector space. When you
So
hear
it's...
algebraists talk about algebras, they mean a vector space, which is also a ring.
So are the two terms related, or is it just like a bad terminology case?
I think it's a bad terminology case.
Yes.
Maybe Alex, there is a connection between sigma algebras and like...
I think you're right. It's basically algebra is an object which has two operations on it, plus and multiplication. In the case of sets, the union is like plus and the intersection is like multiplication. So people are using, so each one of them.
The Boolean algebra analog.
The Boolean algebra, right? So
no, but does that imply closure for complement? And
not automatically. No, not automatically. Just like in algebra in general is not close under star, you know. So then it's a C star algebra. Then it's I mean, every context you take the natural definition, which is slightly different. But algebra in general is something which is first of all a ring. You know that there is multiplication and summation, right? Addition and multiplication. Usually there is some connection, but
there is something called universal algebra also, which is...
No, that's something else. Universal algebra is an object which you can define even more general type of, that there are more than, you have plus, but then you might have several operations. So this is called universal algebra as a general object. Sometimes people, when they say universal algebra, they mean the universal algebra with respect to some category. So it's a kind of something like the free group. I'm not sure if the names are always completely consistent, but they are always related somehow.
Okay, thank you.
Algebra and measure theory in here, you know, they're cousins. They are not more closely related.
They are what?
Cousins.
And not...
Okay.
not brothers.
Not brothers, cousins. Second cousins.
It's an approximation.
Yeah.
No,
but
I think I'll wait a moment for Dorit. Yeah.
It takes time to swallow this, but it's really, you know, after we discussed it a little bit, it's quite a natural thing. You know,
being a hyperlinear algebra, like
no, I mean it's a little, you know, it's a mouthful, but when you come to think of it, if this is supposed to be a substitute for finitely residual, the normal thing you want to say plug the A's and you want to get not zero, but something close to zero. But you need a scale because perhaps you measure in meters, in kilometers, in inches, in what. And delta tells you how to measure in this vicinity. That's essentially all there is to it. It doesn't have, you know, if it's a norm, it's nice, then all the better. But it's really not even important how precisely, you know, you set yourself a standard at every element of everywhere you set yourself a standard. This is how distances or length or numbers should be measured. That's all.
Why is it called hyperlinearity? Just the name?
Okay, Alex doesn't like this name. Like it's supposed to be called hypolinearity or something, and not hyperlinearity, because it's less than being linear, right?
So it's
Alex,
like
maybe you can.
RFT is linearity, and this is like an below version, so hypolinearity, like that.
Yeah, like it's less than being embedded in or being separated using MNC, right? It's a weaker notion, not a strong.
When you say hyperlinear, it's somehow your intuition suggests that it's something better, more than linear. It's linear plus something, but it's actually linear minus something.
It's like approximation of linear, rather, right?
Right.
It can be approximated by
Less
something.
than linear.
Yeah, so I wrote
Every
in
linear
brackets
is hyperlinear.
other names. So it's Hilbert-Schmidt approximable, approximated by matrix algebras with the Hilbert-Schmidt norms. Cones embeddable, it's called many times. So actually hyperlinearity is a bad name, but it's stuck. Okay, let me just start again. So do you have any? Okay, so when you ask it for groups, I'll just spoil you. This is an open question. So are there non-hyperlinear groups is still wide, although MIP star is equal to RE was published, and we will, the question of showing that some algebras are not hyperlinear was settled using this paper. What do you think about, like, can you give me an easy example of a non-hyperlinear in this sense algebra?
Wait, didn't you just say that you needed this paper to find an example?
Oh, so no, but you can find non-hyperlinear algebras because of stupid things, and I'll explain what I mean. So there is this algebra, okay, and I call it the CHSH algebra, and it's highly related to the CHSH game that we talked about last time. And my claim is that it cannot satisfy all the conditions upstairs. Okay, so this is 4 generators. Okay, so 8 because there are also the conjugates, but the conjugates are equal to themselves, so we're back to 4 generated polynomials in these generators and these relations. This is a non-hyperlinear algebra. And the reason for that, if you know what Cohn's embedding problem says, it says that every finite von Neumann algebra is embedded in the ultra product of the 2-1 factor, the hyper finite 2-1 factor. Okay, so this is a mouthful again, but the point is that when you say finite von Neumann algebra, you mean that this von Neumann algebra has a trace defined over it. And my claim is that this algebra cannot have a trace defined on it. Okay, and this is the whole thing. Like it cannot satisfy all these things, because if it could have satisfy all these conditions, it would have a trace on it, and it cannot have a trace on it because of properties that come from the CHSH game, namely the quantum value of the game. Actually, the fact that the quantum value of the game is not 1 automatically means that this cannot be hyperlinear in the sense that we just talked about. This is a result that
Can you explain this? I don't
Yeah. This was way too quick for me.
My claim is that I will today I will give a theorem of Schaffhauser, Kim, and Paulsen, I think. When we'll get to it there, I will give the correct references, that states that there is a connection between this algebra and the quantum value that we talked about last time of the CHSH game. And since the quantum value is bounded away from 1, we can automatically deduce that this algebra is not hyperlinear.
Is this trivial, or is this you'll explain this?
I think we will do a full lecture about it. Like it's a theorem. We need to show like the details, but
so we should consider this just an
advertisement. As a black box for now.
It's an advertisement.
The point is that
fact that we saw that there is a gap between classical and quantum in this game.
Not classical and quantum. The fact that so I said last time that Tselson proved. So Tselson, showed that the quantum commuting value of the CHSH game is bounded away from 1. So it was 1/2 plus 1 over 2 square root 2, right?
Right.
This was the number, and this is strictly smaller than 1. This automatically means, and I will talk about this point, I will explain it, that this algebra cannot be hyperlinear. Okay?
Okay, and is it, you will also
But
explain why
it's not hyperlinear because of a stupid thing. Because the von Neumann closure of this algebra doesn't have a trace. So it's not a finite von Neumann algebra. So it's not a criterion that interests Cohn's embedding problem.
Okay, but you'll explain this point of the trace as well.
Yes, I think we will just do a full lecture about this point. Like, how do you? The point is that if the value is 1, you get a homomorphism onto an algebra with a trace. Okay, like this is the way you should think of it. So the fact that you don't have such a homomorphism, the fact that you don't have value 1 implies that you don't have such a homomorphism, and we will see that later. Okay, so I will go through that point. It is important, but I just wanted to say that at least asking the question this way is not fruitful. Okay, just asking, are all algebras, star algebras hyperlinear? The answer is not no, but because of stupid reasons. Okay, so I will say now that Cohn's embedding problem asks whether there are natural assumptions. Okay, so we will now go through some things, like some consequences of being hyperlinear. Okay, so we will ask ourselves, if you are hyperlinear, what other additional properties this algebra has? And then we will say, okay, if our algebra has all these nice properties, does it mean that it is hyperlinear? And then this is a hard question. Okay, this is my point, that if you add additional requirements over your algebra, specifically having a trace and taking the von Neumann closure inside some bounded the algebra of some bounded operators on some Hilbert space, then it becomes an interesting question.
Okay. This question must somehow be qualified. You cannot throw in all the algebras. You have to restrict yourself to some class. Okay.
Because being hyperlinear induces some other properties that not all algebras have. Okay. This is the point.
Michael, just a quick question regarding delta. Do you know how it behaves with regard to taking a factor? I mean, if you multiply G and G tag by a certain C, you would expect it to reflect in the delta. So
yes, you mean that if I take a Hamel basis of my space or something, I would expect it to be linear with respect to, or not linear, but being scaled by the absolute value of the scalar that I'm multiplying by. I think you must have this property, like it must be true.
Okay, thanks.
Okay, but my point now is that let us now reinterpret this definition with an extra condition that I hide until now. It's a bit technical, but and when we add this condition, it becomes an embedding problem. So instead of thinking about this problem as separating points inside my algebra, every finite set of points, we will think of it as embedding our algebra in some universal object, and being embedded in this universal object implies automatically that you are hyperlinear. This is the kind of idea behind the following. Okay, so the additional technical assumption, and at least for group rings and also for all the CHS, HGM, and so on, this technical assumption is not needed. We assume that there exists some universal constant such that if I separate all the elements of so these AIs, okay, so I send these AIs into MNC, right? Inside MNC, there is this notion of an operator norm. My claim is that I want, in addition to the fact that I'm separating everything and so on, to separate using images of the generators that are uniformly bounded in the operator norm. Okay, so I talked both with Slofstra and I tried to contact other people about how important is this point. So at least for synchronous game algebras and group rings and so on, this is not needed. So when you talk about hyperlinearity of groups, this is not needed to add this technical assumption. And also all the algebras that we actually care about that come from games this is not needed, but to translate this notion into an embedding problem, this is needed. So let us add this additional assumption.
Where do you fit it into the definition? When?
You see that for any f, there exists. Okay, so here is my pen. Okay, so for any f, for every epsilon, there exists an epsilon representation n1 up to ak, such that something, and the operator norm of ai is bounded away by m, and this m is fixed in the beginning. So if there is a function blah blah, so if there exists an m greater than 0 and there is a function blah blah blah, so I add the fact that the images of all my generators are uniformly bounded in the operator norm, no matter how large n is. So, you could have said that maybe you can separate the points, but the operator norm of the images gets larger and larger. So I don't allow you to do it. So I don't call such a thing hyperlinear anymore.
A technical question, but just to verify that I understand. Do you really need this m? Can't you just set it to 1?
It depends on the generators. If the generators are nice enough, so if they are projectors or if they are unitaries, so unitaries is the case of the group ring, projectors is the case of all these games, algebras that come from games, you can just choose one. Maybe it's smaller or equal to 1 and not strictly smaller than 1. But in general, I don't see how you can just ask for any.
Well,
I'll explain why. I'll explain why, Guy, think of the following thing. Say I'm asking you that x star x is equal to 2. This is a polynomial, right?
Fine, yeah.
Yeah, so you expect an image of this polynomial in operator norm, at least either x or x prime, x star to be larger or equal to square root of 2, right? So the operator norm of this thing, you would expect that the operator norm of x is something like square root of 2.
Yes, that's true.
Greater or equal to square root of 2, something like that.
Michael, did you explain, or maybe I missed it, how group rings is a special case of finitely generated C-star algebra or star algebra?
No, I just stated it as a fact that it is, and maybe
but every group or only finitely generated group or
discrete finitely presented. Okay, so let's go for the easy case.
But
okay, anyway, this was a additional.
Why this is a problem, Michael? You just have to define the star operation, no?
Over what?
Of the group ring, yeah, right? And then you take completion if you really want it to be complete. So you take the group algebra over the complex number, and you define the star operation by
just
saying
by inverse.
Element.
The inverse.
But what I was asking is how is it of the forms? How is it finitely generated as an algebra? How is it?
Like,
no. So I take the group to be finitely generated.
Practically, the group algebra is finitely generated.
Yeah. I just asked the group, the original group, to be with this property. Anyway, let's move along. So this was just a technicality. It's an important technicality, and we'll see it in a moment. The point is that we can translate all these kinds of problems to embedding problems, and this is the interesting part. So instead of thinking about being a matrix algebra, okay, so in the case of matrix algebra, it was the definition, right? Being embedded into MNC, right? Being a matrix algebra means you are embedded in something. It turns out that being residually finite dimensional is the same as being embedded in some algebra, a product of algebras, of matrix algebras. And this product can be non-countable, okay, uncountable. But still, there is some product of matrix algebra such that there is an embedding from you to this product. Okay? Okay. And the main question is there a similar embedding problem that defines hyperlinearity? And this is the topic of the rest of the talk. So we are going to construct some kind of an object that being embedded in this object is the same as being hyperlinear with the technical assumption that I added at the end. Okay? Okay, so you can check that, and this is what Alex said before, that you can, okay, so you take the product of all, a product of matrix algebras. You think of Alex's definition using a sequence. So you take a sequence of epsilon representation, epsilon n representations, where epsilon tends to 0, epsilon n. And then you take the n by n matrices that you get, you call them ni, okay, ni, or, so epsilon I and ni. So we get a sequence of epsilon I representations such that epsilon I tends to 0. Okay, so these epsilon I representations have some dimension. So the elements are sent to ni by ni matrices. And the claim is that every such sequence lives inside this product. So every element, every generator of the algebra is sent to an element of this product. Okay, and if you divide, the point is if you divide by all sequences such that the limit of the Hilbert-Schmidt metric in the sequence is 0, this just means that this is actually an embedding now, right? So, and it's not an embedding now, it's a homomorphism. Okay, so beforehand, if you don't divide by this criterion, you don't get a homomorphism. So I wrote here that I will write a proof. So let me just write it in a more specific way. So choose F1.
Which direction are you proving?
Being hyperlinear implies being embedded in this thing. Okay, so I prove this direction. Okay, the other way around is not also quite clear, but I'll at least prove this direction. Okay, so we choose finite sets, F1, F2, F3, and so on, such that the union of the Fi's is dense in U. Okay, now what does dense mean? It's a vector space. So I can just ask you to be dense under some Hamel, what do I need? Maybe I need something, I need to be a bit more careful, but I want to be dense inside this algebra, okay? I need to think for a moment.
So it's not clear what it means, and is it clear that U is separable?
I think that
there was no topology. We
didn't
have
yeah,
topology.
okay, so let me explain how can I do it in a way that there exists something, okay? It's the, we have C star of x1 up to xk, right? Our algebra is a projection of this thing, right?
Yes.
Okay, so I can just take the basis of all monoms inside this algebra. I need, oh no, okay, so any, what can I take? I can take something like Q, Qi, x1 up to xk or something, right? And now this is countable. So I just take finite sets, and this is dense in the correct way that I want, okay? So this is good enough for me.
What is Q square I?
It's the rationals with I inside C.
It's like A plus IB, where A and
A
B are
plus
rationals.
IB, I, A plus BI such that A and B are rational.
The usual, yes, okay.
Yeah, and I'll take polynomials only with them. Okay, so this is dense enough for me. Okay, so the point is that I can choose this, okay, for example, way of taking something dense inside U. And now I want to, I'll take epsilon representation. So I'll take epsilon 1 representation that separates, I think, F1, and I take epsilon 2 rep that separates F2, and so on. And then I'll get this sequence.
Epsilon n is 1 over n or something, right?
Okay, so I'll take, yeah, okay, so epsilon I is something that tends to 0. Doesn't matter exactly how fast, but you can choose it to be anything. Yes.
Okay, Okay, just going back a little bit, but did you mention what type of sequences you take in this product before dividing?
Yeah,
Like
now I'm stating what are the sequences. Okay, so here I have A11 up to A1K. No, AK1. Here, this is what an epsilon1 representation means, right? So I take A11 up to AK1. Here I have A12 up to AK2, and so on and so forth. So I'll have, in the epsilon I case, I'll have, and now I'll send AI to the sequence AI1, AI2, AI3, and so on. So this is an infinite sequence of matrices.
Yes.
Now, at least for now, this is not a homomorphism, right? So the fact that I sent it there, they don't, they do not respect multiplication or addition or anything. They're only approximately doing that, but it gets better and better in the Hilbert-Schmidt norm when you go through the sequence, right? It gets closer and closer to being an actual homomorphism. So now I'm stating that every element of this product, this product is just a set of sequences. So every element of this product who is a sequence whose Hilbert-Schmidt norm tends to 0, I'm modding out by this sequence. Now, I'm a bit cheating here because this is not an ideal. At least in this case, this set is not an ideal. What I need to do for it to be an ideal is exactly the technical assumption. So I need to take not the product of all matrices, okay? So, but only sequences of matrices that are uniformly bounded in the operator norm. Okay, so again, this is just a technical thing. We want this thing, okay, I'll mark it by red. We want this set to be an ideal, so we can have a quotient of the algebra, and then we will get an actual homomorphism to an actual algebra. The point is that we cannot do it if we don't take some restriction on these sequences, and the restriction is exactly taking sequences that are uniformly bounded in operator norm. And this is preserved under multiplication and under addition. So this is a subalgebra of the original algebra.
So just below when you wrote AI, you mean the generator of the AI is the ith generator.
U is finely presented algebra, so
yeah.
AI is
so it's like XI. It's supposed to be XI.
No.
Yeah,
right. Okay,
there's
sorry.
a problem with indices.
I call it XI.
There's a mix of indices, right? I here on one hand is AI, which goes over the generators.
Right, you're right.
And I goes also over the sequences. So
yeah, you're right. Maybe I'll call it XT, and this is the Tth generator. Okay, you're right. So I is the upper index here is the I, and it tends to, and the epsilon I tends to 0, and the lower the subscript is just the generator of the algebra. Thanks, Dory.
Okay.
Anyway, the point is that now we had a function from, actually not from U, right? We had a function from the set x1 up to xk inside U. So we had a function from this to this product of matrices, M, N, I, C. And my claim is that now I divided it by some ideal. Okay, so now this is a bounded, so I'll call it bounded. Okay, and I divided by some ideal, and now the point is that since we were using a sequence of epsilon I representations such that this epsilon I tends to 0, now this is an actual star homomorphism. So you can extend now for this algebra, it satisfies all the relations, okay? And now it's a star homomorphism. You can extend it to a star homomorphism into this algebra. Okay, so this is a weird construction.
But you need to check that it's an embedding, no? That it's injective. You need to check.
Okay, so the fact that it is injective comes exactly from the delta that we used beforehand, right? And we need some, and now I need to say something about the denseness, right? So because of the, I didn't take any element of the group of the algebra before, right? I took only a dense, like the union of all the FIs is only dense.
Yeah.
So, but now you say that, okay, it's close to two things that are separated from zero and just use linearity or something and it's bounded away from zero, okay?
It sounds convincing.
Yeah, so you need to say something like that, but the point is that you can, okay? Okay, great. So we were able to construct, now we have this monster that we constructed, which is an algebra. And being embedded in this algebra is the same as being hyperlinear. We have a few problems with this algebra. The first one is that we cannot control the sequence Ni. Okay, so this sequence can be quite, like for different use, this sequence can be very different. So this is highly non-universal. It's not for all use, it's just for the specific U. And it also depended on the specific choice of the FIs, right? So this is one problem. And also, there is no natural...
Sorry, problem for what? I didn't understand. A problem...
We want some universal object, Dorit, that will work for all use.
Why don't you just take M1 times M2 times M3? Why? What holds you from doing that?
The Ni's depend on the U. The sequence of N's depend on the U. So I'm just stating that maybe I can take something that is independent of the Ni's, like independent of U. Some product of things that are independent of you. Okay, no, you would have want to say something like.
Michael, I'm pretty sure you can, because assume you have a very sparse sequence, then just kind of enlarge it in an artificial way by embedding the n by n matrices into the n plus 1 by n plus 1 matrices and add more homomorphism, and so you can take.
Okay, Alex, this is a good point. First of all, Alex, so first of all, is there a star homomorphism between n by n matrices to n plus 1 by n plus 1 matrices?
Yeah, so it's the same problem that we had with the first example of a homomorphism, that you needed AA and A0 or A1 didn't work.
Yeah, so this is one problem, and I will fix it in a moment. You are right. You need to be a bit careful in the way you embed things in one another, because you want things to be embedded in a way that preserves the Hilbert-Schmidt norm. You want, in some sense, all the things coming from the Hilbert-Schmidt properties not to be ruined using your embeddings. So we will fix it in a moment. So just go with me. I will fix it just now.
But didn't you give an example where you can embed AN in A2N or something like you did this?
Exactly. This is what I'm going to do now. Okay, so just be with me.
2 by 2 into 4 by 4. That was
and then we will embed it into 8 by 8 and 16 by 16. But now there's a problem. What do you do with 7 by 7 matrices? You cannot embed them into anything. But there is a way to solve this as well. So just again, be with me for a moment. I'll fix everything. So we would have liked to just define something like,
Let me just say one thing, which I think is what confused Dorit, which is the goal. The goal is to say that U is whatever, I forgot the abbreviation.
Hyperlinear.
Hyperlinear, right, no abbreviation. We want to say that U is hyperlinear if and only if it embeds in blah.
Something. Yeah, right.
And so forth,
you want a very
don't have a single blah for all use.
Right. So we construct this blah.
Of blah. That's what we're doing now.
Right. Yeah. Okay, so let's first of all tackle the fact that these Ni's are dependent on the U. So we would have liked to have some union of matrix algebras and say that you just embed in the product of these, but the problem is that there is no natural definition of such a thing, such an object of M infinity C. And the way we fix it is that we take the direct limit, if you know what the direct limit is. We embed M2 by 2 into M4 by 4 into M8 by 8. The point is that this preserves the trace, the normalized trace. This is what I said when we talked about this embedding. And thus it preserves the Hilbert-Schmidt norm. And then you can think of like infinite matrices, but that are constructed using copies of 2 to the n by 2 to the n matrices on the diagonal. Okay, so this is a subset of all operators on infinite sequences on the L2 of n, for example. Okay, but it's a very specific embedding, and the specific embedding has a Hilbert-Schmidt norm on it. So it has a normalized trace and has this nice property. And we call this R0, okay? So this limit, the direct limit of these 2 to the n by 2 to the n matrices with this specific embedding in the diagonal, we call it R0.
Michael, how does this take care of 7?
Oh, this is a good question. The point is that although, okay, so what do you take? You want to be, you cannot embed them in an actual way. But what do? You take the blocks of 7 by 7, okay? So many times such that if you add some zeros here, a small number of zeros here, it's a power of 2, right? And now it's not an exact embedding and it's not a star homomorphism, but since everything here is approximate, it's okay. And for every epsilon, you need more and more copies, right? But again, you can do so.
Reminds the joke about the Israeli hill, right? 100 degrees is not 100 degrees. It's, okay. That's exactly, roughly, you know. Okay.
Yes. So since everything is approximated here, these kinds of embeddings are okay for us, are good enough for us. Okay, so now we have a different definition. And again, this is not R naught of n, this is R naught of n bounded. Okay, so again, I take only sequences. Here we have, again, the notion of an operator norm. It acts on L2, right? So we can define what being a bounded operator is. And we can, again, ask the whole sequence to be uniformly bounded. Okay, so again, the same thing. So the blocks in these matrices need to be bounded uniformly.
When, I mean, we choose 1M for the whole thing? The bound on the bound on the operator.
It's not all the whole algebra, it's on the set of generators. So this is a finite set, right? So if, for example, if all the generators are unitaries, as in a finitely presented group, so in a finitely presented group ring, this is, you can just take it to be 1 or something. And if these are all projectors, you can also take them to be 1, but in general, you need some universal bound, a uniform bound. Okay, so the problem is that we still don't have a definition of a trace over this algebra. So this algebra, so so R naught have a notion of a Hilbert-Schmidt norm, but this object potentially doesn't have a notion of a Hilbert-Schmidt norm on it. And we want this large object to have a notion of a Hilbert-Schmidt norm. So having a trace and all of this. How do we fix that? We use something called ultra powers. Okay, this is just a trick of logicians that is now used very frequently also with algebraists. And you have, for any such sequence, you have the sequence of traces of the elements, right? Okay, so the trace of the block, the normalized trace of the block is the way I define the trace. And now I just want this sequence to have some limit. So again, I'm now just using the operator norm, bounded operator norm. So the trace is bounded by this uniform bound on the operator norm, because the trace is just, the normalized trace is just the ממוצע חשבוני, arithmetic
mean.
Yeah, arithmetic mean of the eigenvalues, and the operator is, it's not the maximum, but it's the maximum of the adjoint times the matrix itself. So anyway, this is a bounded sequence. now the trace of the AI is a bounded sequence, and I want it to have a limit. And the ultra filter using ultra limits enables us to somehow, in a magical way, define a limit to every such sequence.
Do we need to understand these words? I don't know what ultra.
No, we just need to believe that there is some magic that comes from logic that enables you to choose for any such sequence a limit. And the point is in a consistent way. So
this has nothing to do with algebras. It's going back to Banach, I think, or something like that, or even before, that there is a kind of a trick to define a limit to every bounded sequence of real numbers. That's all.
Yeah.
If you take a sequence, which is AI, so that AI is equal 4 on the even number and 5 on the odd number. So in a normal calculus class, you said that it does not convert. There's no limit. In this, once you fix an ultra filter, it has a limit.
Instead
I
of
cannot
saying
tell you if it's 4 or 5. It depends what is the ultra filter. But once you fix an ultra filter, there is a limit.
I think for people that don't come from logic or algebra, instead of saying ultra filter, there is the Banach extension theorem or something. The limit is the limit of a function. The limit of a series, sorry, is functional. It's a linear functional that is defined on the sequences that actually have a limit, and which is a subspace of the set of sequences in general. And Banach says that you can extend this functional on everything in a bounded way. So that's it.
Without increasing the norm.
Yes, right.
But you cannot guarantee that it's multiplicative that way.
The trace is multiplicative. I don't think the trace should be multiplicative.
The extension, you have to also guarantee that it's multiplicative. You need an extreme point to what you said. That's another discussion.
This Banach extension theorem, you know, for us, I'm talking now to the computer scientists, is essentially LP duality. Linear programming duality. This is what it is. So yeah, you're looking at the space of all operators, and somehow you take an extreme point, and this does the Banach extension theorem.
Yeah, or you just
okay. Let me maybe. Okay, so this is a fruitful discussion, but I am -2 minutes, and I want to just say a few more things, and we will go home. So maybe let me go through 2 more slides. And the point is that, is this now a good enough object? Okay, this R is not to the power of U. The answer is no. And the reason is that you can define topology, many topologies on the bounded operators of a Hilbert space. This space have an action on a Hilbert space, but it is not necessarily closed in the topology that interests us. Okay, so this is a point. So you can define many topologies on the bounded operators. There is something called the weak operator topology. And I'm claiming, and I'm not saying anything about it now, that this R not U acts on some Hilbert space. This Hilbert space is not separable as opposed to the Hilbert spaces that we discussed last time. But it still is, it has some action on some Hilbert space. So we can think of the elements of this algebra as elements of BH for some H. And now that we think of them that way, we can close them under the weak operator topology of this space, whatever this weak operator topology means. And now, from now on, we call this R to the U. And this is called the ultra power of the hyperfinite to 1 factor.
Are you going to repeat this next week?
Yeah, but Cohn's embedding theorem asks... Problem, right, not theorem. Asks whether any algebra that has a trace on it and is closed in this weak operator topology and is already embedded in some algebra of bounded operators. So we have already an algebra. It's embedded in the bounded operators on some Hilbert space. It is closed under this topology called the weak operator topology. And it has this notion of a trace, this idea of a trace. Can it be embedded in this R to the U? And the point is that everything that embeds in this R to the U has a trace on it. And the CHSH that I showed you before cannot have a trace on it.
So
you can show that
it's bad example that you presented before, that you told us.
Yeah, exactly.
So,
It kills the bad example, the example, because this notion of being finite for Neumann algebra just means that you have a trace, and this algebra cannot have a trace.
Okay.
And now we can say that this is Cohn's embedding problem, but a more specific problem is asking this question about finitely presented algebras that has a faithful tracial state on them. No matter what it means, we can just ask if this finitely presented algebra already has a faithful tracial state, does it mean that it is hyperlinear? And now this is an interesting question. And this is the question that the MIP star is equal to RE by G, Natarajan, Vidic, Wright, UN solved.
In negative.
Can you say a word about a faithful tracial state in the words of von Neumann algebras? What do you mean by that?
Okay, so say again what I need to say, and maybe I'll give someone else to say it.
Can you say a word about what's faithful tracial state in the word? If I understand a little bit about von Neumann algebras, can you say something about it?
So I think being being a state, I think Dorit, this is the part that you don't need an explanation about, right? Okay, so it's some functional from the algebra to the complex numbers, such that it's positive and it's unital and it's tracial, which means, okay, so there are something like 8 criterions that this functional needs to have. And if it has all this condition, it's called a tracial state. And then if it, in addition, there is something called the GNS representation of the algebra. If in addition, the GNS representation of the algebra is an embedding, if you embed your algebra to the representation is an embedding, you call it a faithful tracial state. Okay, I think if you want more details, Alon maybe can just automatically give you more, but just wait a minute, Alon. I think if there are more questions about what happened until now, I think this is the time, and then we can stay for a few minutes and discuss this point. Okay, so I'll just say about next week before the questions that I'll explain what the connection with the games is. So I will give a theorem that states that if you can construct a game with specific values, quantum commuting values, and quantum values, you will automatically give a contradiction. So you will construct such a finitely presented algebra with a faithful tracial state that is not embeddable, not embedded in R to the U. So we will see how to construct such an example using games. Okay, Uriel, you wanted to ask something, or so you?
Oh no, I have a lot of things to ask, but I think it's too much. But